Welcome back. Today we're going to continue working with exploring exponential models. So yesterday we began with the basic growth and decay models. Now, a special type of growth model is what we call compounding interest. Now, why I think this is really interesting and something you guys will enjoy is because this is exactly what banks do to your money. This is what's happening every day across the country, around the world, with all of our money. So let's take a look at what's going on. So this p-value right here, that is the principal amount or the initial amount. That is the money that you are giving the bank, that you put into the account. As always, the rate is going to be just whatever the interest rate is, okay? 3.4%, whatever. And again, remembering, we always use it as a decimal, just like before. You know what T is for time. So how many years is it in the bank for? Now, the new term that you probably don't know, N. So N is the number of times the interest is compounded per year. So that's where the word compounded is coming in. So let's take a look at that blue text down here. So if it's compounded annually, so meaning compounded once per year, what's that doing? Well, that means that you use an N of 1. Semi-annually means it's being compounded twice a year, so N would be 2. Quarterly would mean 4 times in a year. What the compounded means is the number of times that they calculate your interest, and it's called compounding because every time they calculate interest, you're making interest on your interest. So that's what that compounded means. You're compounding that effect because now you're making interest on that interest that you already have. So that's where that term comes from. And again, this formula, not too terribly different than the growth, just has that extra little n in there that we need to account for. So what are we going to do? Well, it's really similar to what we did yesterday. You identify P, N, R, and T. Now, again, this time we're talking about 4 things, but that's okay. Second, type it into your calculator all at once, all right? I want that whole thing just shoved into your calculator. With the stipulation that you put your parentheses around that 1 plus r over n and that exponent, nt, that will also need parentheses. Then for monetary values, we usually round to 2 decimal places unless the problem states otherwise. So let's dive right in. Let's see what's happening. So an amount of $1,500 is deposited in a bank paying an annual interest rate of 4.3%, compounded quarterly. What is the balance after 6 years? All right, so I'm going to go through and I'm going to identify each and every one of those pieces. So my principal amount, that initial value, is that 1,500. My R, my rate, is 4.3%. But again, we can't leave it as a percent. We have to move that decimal place over twice and get 0.043. My N, well, it says it's compounded quarterly. So if I look up at that text, quarterly means an N of 4. It's being compounded 4 times in a year. And then finally, how long is it going in for? 6 years. All right, so I have those 4 things labeled out. I've picked out all the information. Now it's time for me to plug it in. So I put 1,500 out front, 1 plus R over N. So 0.043 over 4. And in the exponent, N times T, 4 times 6. All right, now again, This is one of those things, if you type it in all at once, with those parentheses, order of operations will resolve itself and it'll turn out properly. But again, the important thing is you must type it in exactly as it's shown. So please pull your calculator out. Do this calculation with me to make sure that you are getting the right answer. So pull out your calculator, try this out. What you should get, $1,938.84. But again, I can't stress enough how important it is that you know how to use a calculator for this. If you just write down my answer without checking that you can get it yourself, come test time, you may really be hurting if you're typing it in wrong, and I can't help you at that point. So again, please make sure, pause the video if you need a little bit more time, but check that number. Make sure that you yourself can get that number. So that same $1,500 is deposited in a bank, paying the same annual interest rate of 4.3%. But this time, it is compounded monthly. What is the balance after 6 years, and what observation can you make about your money as N increases? All right, so we're depositing that same $1,500 with the same rate, the 4.3%, but we use 0.043 because that's its decimal form. But this time it's compounded monthly. So how many months are there in a year? Well, there's 12. So that means it is compounded 12 times in a year for the same 6 years. So what's the point of this problem? Well, the point of this problem is I changed n, all right? I'm using all of the same information. However, I'm changing my n so I can see what is n doing to my equation. So let's plug everything in. 1,500, 1 plus 0.043 divided by 12, then up in the exponent, n times t. Now, again, please follow along. Please try this out in your calculator to make sure that you can get the same answer that I am about to get. And what you should get, 1,940 and 61 cents. And I want you to note, how does that compare to our previous answer? Well, our previous answer was $1,938.84. Our value went up. The more times that it gets compounded in a year, it looks like the more money we're going to make. Now, why does that make sense? Well, again, the way I explained compounding. When you're compounding interest, you're making interest on your interest. So the more calculations of the interest you do, the more opportunity you have to make money off of the interest that you've already made. Again, really wordy, but hopefully it makes sense to you where that's coming from. So let's jump down to our next example. Suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? All right, so again, let's pick out our information. Our starting amount, the money that we're handing the bank, is 500 at 3.5%, but again, that's not useful to us. We want 0.035. Now, it doesn't say anything about being compounded. So when it doesn't use the word compounded, we're going to assume that just means once in a year. Compounding annually is the same thing as not using the word compounded at all. And we're talking about 5 years. So let's take a look at this. 501 plus r over n, so 0.035 over 1, in our exponent, 1 times 5. All right, now I do want to show you something here. So notice all those ones really aren't doing anything in our equation. So I want you to look. When it's compounded annually, when that n value is 1, don't we just get back our very basic growth equation? So that's why this fits so well after what we did yesterday, is because this compounding case is just an extrapolation of growth. Okay, because the most basic form, that annual compounding, is just the basic growth equation. All right, so that's something I want you to see, is that it is very connected. It is the same thing as a growth equation, just happens to have that n in it. Otherwise, it actually does turn out to be the same equation. So let's calculate that. And if you check your work on the calculator, you should get $593.84. All right, now there's one more type of question that we can come across. How long will it take you to have $700 in that account? So now we're not given a time. We are looking for the time. We're given a final amount. We're given that we want $700 in that account. So what are we going to do? Well, we're going to make a table to test that strategy. All right. So we're going to make a table using different t's to get different final amounts. Now, do we have to start all the way at 1? Now, in this case, I'm going to say no. Let's think about why I'm saying no. Because we're looking for $700. Now, we've already calculated where t is 5. And when t was 5, it was $593.84. So do we need to check anything less than that? No. We want to be checking the values greater than that, because we already know we need a longer time frame. We need a t greater than 5, because even that only had less than $600, and we're looking for 700. All right, so this means we need to check when t is 6. So that means plugging 6 into that equation. And again, if it makes you more comfortable, you can go all the way back to that. Otherwise, remember, those ones really don't matter right now. So let's see what this gives us. When I plug in 6, it gives me $614.63. Okay, so I'm not quite there yet. Haven't gotten there. Well, let's try after 7 years. How much money do we have after 7 years? After 7, I've only got 636 and 14 cents. All right, so 7's not what I'm looking for. Let's try 8. Let's see what's happening after 8 years. Well, I'm getting closer, but I'm still not quite there. I'm only at $658.40. Now, this doesn't seem to be increasing very quickly, but we do want to make sure that we're careful and we check each value. So let's check 9. I plug in 9, get $681.45. So we're getting very, very close. And finally, let's try 10. When I plug in 10, I finally hit over $7 or over $700. All right, so this is when t equals 10. We got that. Now, I want to think about it. You earn interest in discrete amounts, right? So in this case, we're getting that interest once a year. So you'll have to look for a year where your bank account first hits over $700, but notice 700 wasn't actually in our table. So to answer the question, when will we have $700 in the account? Well, we'll never have exactly $700 in the account. We have to wait till the first year that it hits over that amount. So how long will it take to get that? We have to wait 10 years because that is where we finally see a value that is over 700. All right. So that is going to be all for our notes today. Thank you for joining me. So please make sure you have all of this written down, and then please come back prepared to do practice work in class.